Hey everyone, Mr. Dow once again. Today we're talking about implicit differentiation. Today we're going to do this problem, x squared plus y cubed plus 2y squared equals 8. And I'm trying to find the derivative dy dx. The problem with this one is not solved for y. It doesn't say y equals. I'm going to have to differentiate with respect to x as if y is a function of x. And here are these steps. So I'm going to go ahead and take the derivative of each of the items in the expression, d over dx of x squared, and so forth. The derivative of x squared is 2x, and the notation here is I took the derivative of x with respect to x, dx over dx. The derivative of y cubed would be 3y squared, but I took the derivative of y with respect to x, and I notate that dy dx. Take the derivative of 2y squared, which would be 4y. I took the derivative of a y variable with respect to x. I notate that afterwards dy dx. And take the derivative of a constant, which is 0. Everywhere I see dx over dx, I can just remove those. Anything over itself is 1, so dx over dx drops off. And of course, 0 times dx over dx is still 0. I'm going to subtract 2x from both sides to keep all the y variables on the left, the x variables on the right. Now I'm going to factor out a dy dx, leaving me with 3y squared plus 4y. Divide both sides by 3y squared plus 4y, and I have dy over dx, the derivative, negative 2x over 3y squared plus 4y. Example 2. Find the derivative dy dx if y squared equals x. I'm going to take the derivative of each item, d over dx. The derivative of y squared is 2y, dy dx, because I took the derivative of a y variable with respect to x. And on the right side, the derivative of x is 1, and I took the derivative of x with respect to x, dx over dx. Dx over dx cancels out. Divide both sides by 2y, and I have the derivative dy over dx is 1 over 2y. Problem 3. Find the derivative dy dx of the following expression. I'm going to take the derivative with respect to x of each of these three items. With the proper notation, the derivative of 2y is 2 dy dx. The derivative of x squared, 2x dx dx. And if you recall, the derivative of sine is cosine, and the variable is y, dy dx. Dx over dx is 1, that cancels out. And I'm going to reorder this. I'm going to subtract cosine y dy dx to both sides to get all the y variables together. Factor out dy dx. Divide both sides by 2 minus cosine, and I have my answer. Here's the next problem. Take the derivative dy dx. d over dx of all four items. Here I am going to have a product rule. The derivative of x to the fifth is 5x to the fourth. I'm going to leave off the dx since we know it's going to reduce to 1. And the product rule is going to be applied with my 4xy cubed. So you can see the product rule being used here. It's take the derivative, leave it, plus leave it, take the derivative with the proper notation. The derivative of y to the fifth and the derivative of 2. clean up the brackets just a little bit. Move some items around. I'm going to move the 5x to the 4th to the right, 4y to the 3rd to the right by subtracting. Factor out dy over dx. Divide both sides by 12x y squared minus 5y to the 4th, and I've solved for dy dx. Example 5, find the second derivative, d squared y over dx squared. I'm going to have to use implicit differentiation twice, perhaps. Take the derivative of all three of these items. Proper notation using dx over dx cancels out for 6x squared. dy over dx, the derivative of a constant is 0. Subtracting 6x squared and then dividing by negative 6y, 6's cancel out, I'm left with dy dx equals x squared over y. That's the first derivative. To find the second derivative, I'm going to take the derivative of the expression in purple, d over dx of both sides. d times dy is d squared y. dx times dx is dx squared. Take the derivative of x squared over y. I'm going to be using the quotient rule. Everything you see in blue. I'm going to separate the numerator by putting 2xy over y squared and x squared dy dx over y squared. Here I can do some substitution. I know what dy dx is. In purple, we solved it for x squared over y. So after substituting out the expression dy dx, I would have x squared over y in the same expression. Combine like terms with the x squared times x squared over y would be x to the 4th over y. Multiply by the reciprocal 1 over y squared. I'm trying to algebraically reduce this. And I get my final answer, d squared y over dx squared. Let's do an application problem. I'm giving you an equation. I want to find the slope of the curve at a given point. I'm going to have to take the derivative, or find the derivative, and then evaluate the slope using the derivative. d over dx of all four in the expression. The derivative of x squared gives me my 2x dx. I didn't write dx over dx. And then I have a product rule with xy. The derivative of y squared is 2y, and that's dy dx. Cleaning this up a bit. I'm going to subtract 2x and subtract 1y to get x and y on the right. Divide by x plus 2y after I factored out dy dx, which I skipped there. And now I have my expression for the derivative. I'm interested in evaluating the slope at the point 1, 2. So I'm going to evaluate dy dx in green here at a point 1, 2. I'm simply just going to plug in a 1 everywhere I see an x in the expression in blue, a 2 everywhere I see a y in the expression in blue. Reducing everything in green, I'll get my final answer where the slope will be negative 4/5. And there you have some good examples on implicit differentiation.